B, discovery of the photoelectric effect and development of the quantum model of light is made by Einstein. And D is to work on the effect of temperature and black body radiation intensity. That is Wien's law. So A is the right choice.
Okay.
Question 2, black body radiation provides key evidence for the quantum nature to the behavior of black body radiation. So C will be correct, as
got
C
that.
says Planck resolved the UV catastrophe by assuming that electromagnetic energy is quantized. Yeah?
Yep,
Yeah,
got that.
and the other choices are like wrong in some way.
Yeah,
Question
they're
3,
wrong.
what is the energy of one photon emitted by a laser of wavelength 600 nanometer? How can you get this wrong? It's pretty easy, yeah? So energy of a photon is proposed by Planck is just Planck's constant multiplied by frequency, or Planck's constant times by speed of light over the wavelength. Yeah?
Yep.
So what you
got
should
that.
get is you should get B.
B, yeah.
Question 4. The graph shows curves predicted by two different models, X, Y, for the electromagnetic radiation emitted by an object of the same temperature, which is correct. So model X was the UV catastrophe, right? So it's like that's the classical model which failed to predict behaviors of black body. Model Y assumes energy is discontinuous. That's how we resolved the UV catastrophe, was by assuming light has quantized energy and is supported by experimental evidence. Yep, so B is right. Okay.
Yeah.
Question 5. A black body has a temperature of 3000 Kelvin. What is the peak wavelength of radiation emitted from this black body? So you've just used Wien's law?
Yep.
So, yeah. So use Wien's law, rearrange for the wavelength, right? You get D. Question 6 is photoelectric effect. Light of wavelength 450 nanometers is shown onto the surface of calcium, which has a work function of 4.65 times 10 to the power of negative 19 joules. Which row of the table correctly identifies the experimental observation and the model of light supported by the photoelectric effect? So we've got 450 nanometers incident onto a calcium. So you want to check that if this light passes the threshold frequency.
Nope.
Yeah. So if you did that calculation, you should see that the energy of this beam of light, or of each photon in this light, does not exceed the work function. Okay, which means photoelectric effect will not happen. And this is supported with quantum models of light. Okay.
Yep. Yep, got that.
Question 7. It's again the photoelectric effect of two lines representing different metals of their kinetic energy of photoelectrons versus frequency. When light of the same frequency and intensity is used to irradiate on both metals, so like if I just pick a frequency that both of the metals has photoelectrons and draw a straight line, you can see how kinetic energy for metal 1 is much larger. So A is correct. Okay. Question 8. When light of specific frequency strikes a particular metal surface, photoelectrons are emitted if the light's intensity is increased but the frequency of light remains unchanged. Which row of the table is correct? So the number of photons emitted, where would represent the intensity. If light's intensity is increased, but the frequency remains unchanged, right? So we just more photo. So A.
Yep.
And maximum kinetic energy of the photoelectron, because frequency is kept constant, so would remain the same. Yeah. There's one soft collision of a photon colliding with an electron. Question 9. In a photoelectric effect experiment, light of wavelength 700 nanometers, a current reading was observed in the galvanometer connected to the metal, was also measured. The experiment is repeated using light of wavelength 400 nanometer and the same intensity. Okay, as the 7 nanometer light source. How will the current stopping voltage change? So you see how we have swapped our light to a smaller wavelength? Yeah.
Yeah.
While
So the
keeping the
voltage,
same intensity.
so
So
the
what is the
voltage will change. Yeah.
intensity?
Intensity is like
Yeah.
how, oof, like basically how many like
So
the
intensity is
photons are
technically, yeah,
emitted at the same time.
that's right. So intensity is how many photons, but it's also related. So intensity is intrinsically the power over some area, right?
Yeah.
So if we change the wavelength of the photons without changing its intensity, that's sort of saying that we are emitting more energetic photons in the same energy output. That means we must, although intensity are the same, but see how the energy has been changed, which means now we have to emit less photons of higher energy, right? So the photons are going to be less for the 400 nanometers one because the same intensity. Okay,
Yep.
that means the photo current will change as well. Okay, so B is the right answer.
Yep. Got that.
Question 10. When a source of light is used to irradiate a particular metal surface, a reading is observed in the galvanometer, which action will increase the magnitude of the current. So here, be very careful that the voltage is applied in the forward direction. So here is positive, here is positive, here is positive, is negative, is negative.
Okay.
The photoelectrons emitted will be accelerated instead of decelerated in our original experimentation. So if we want to increase the magnitude of the current, we
Make it
could
brighter.
increase the brightness of the light, and that makes sense. Yeah. If we increase the voltage supply from the battery, what does that change? That just changes the energy of each electron.
Yeah.
Right? It just accelerates
Okay.
the electron, but the current is only proportional to how many of those electrons are.
Yeah.
So using a blue light doesn't help replace the metal with a smaller doesn't help, only B helps, okay?
Yep.
Question 11. Light of wavelength 500 nanometer is used to irradiate copper in an evacuated tube. This means just a vacuum tube, okay? So the copper and the collecting plate are connected with a battery. This is again a forward potential, so it's accelerating those photoelectrons. What is the minimum voltage required for a current to be detected? So you want to detect a current, yeah? For a current to be detected in the galvanometer. Yeah, so this question is kind of different to how we used to do the experiment. What we used to do the experiment is that we put a voltage to stop the current, but now it's sort of like we put a light that doesn't have enough energy to overcome the work function, but then I would put some voltage to reinforce the escape of electrons.
Yeah.
So it's really like EK. So we want just current to be detected. Minimum voltage, so EK is like 0, which is the energy of light minus work function. It's not enough, but we add some voltage. So Q times this voltage.
Okay. And then
you will solve for that. Yeah, so it's
yeah.
really a weird process. If you did that, it would be A, okay?
Yep.
Question 12. What is the peak wavelength of electromagnetic radiation emitted by a star with a surface temperature of this? That's just Wien's law. Be careful to use Kelvin, okay?
Yep. Okay.
Should be D. Question 13. Two stars observed from Earth. Their visible light spectrums are as shown. Using these spectrums, we did this question, right? So it was C.
Yeah, we did.
Because just once again, star X is a thicker line, means it's rotating. Star Y has the lines systematically shifted towards red,
Yep.
which means redshift, which means the star is moving away from us, experiencing this Doppler effect. Okay.
Yep.
Question 14. A light produced by which setup will form an emission spectrum when passed through a glass prism. So glass prism is like a diffraction grating that splits light at different angle. We want emission spectrums. We want to heat up a sample of gas in the enclosed tube so that electrons are excited and they jump back to emit light. A will be the right choice. B,
Yep.
which says sunlight after passing through a polarizer This doesn't help. Sunlight is
Yeah.
black body radiation. C says a gas discharge tube with a electrode connected to a low potential difference. Low potential difference will not have enough energy to excite those electrons, so will not happen.
Yep.
Incandescent filament is also black body radiation.
Mm-hmm. Yeah. Okay.
Question 15. Spectra from star with similar chemical composition can have absorption lines with varying wavelengths. Okay. This suggests that the star have a different rotational velocity or like density. Okay.
Mm-hmm.
That's what it's about. So density is like a blurry broadening effect, while rotation is a sharpening broadening effect. Okay.
Yep.
Question 16. Question 16 says, which row of the table correctly describes the nature of the spectrum of light produced by an incandescent filament? It will be a continuous spectrum, and spectroscopy uh, for incandescent filament, incandescent lamp works by heating up a big resistor. There's no electricity light, so it's technically not a spectroscopy event. Okay, so just
Mm-hmm.
black body radiation. Does that make sense to you?
Yep.
All right, question 17 was been through. It's just electron go from higher energy to lower energy, and then the sum of energy W and Z becomes X. Okay, it's pretty trivial. So A
Yep.
is wrong. So these transitions will produce absorption
Mm-hmm.
spectrum. These are emissions, right? As electrons jumping from higher to lower emits photon. W produces a shorter wavelength of electromagnetic radiation than X. So W has weaker energy than X. X will be producing a photon of higher energy, which means a shorter wavelength. Okay.
Yep.
C says electronic radiation produced from all transitions will have the same intensity. This is also wrong, but you don't have to know this for high school. It's more
Mm-hmm.
preferable for transitions that are like at smaller energy states. So W will be more preferable. They're not gonna
Okay.
have the same intensity. Okay.
Okay.
In continue, question 18 says to consider a light of wavelength 640 nanometers. Calculate the energy of photon of the same wavelength. You just use Planck's equation. It's pretty
Yep.
easy.
Got that.
Okay. Question B says to distinguish between Newton's corpuscle and Planck's concept of photon. It's a extended response. So both models sort of indicates that light is made of particles, but the quantum model is more than just particles, right? It's more like a wave particle duality thing. Okay.
Yeah.
So you have to make this distinguishment. So what I said is, I said Newton's corpuscular model. So I define it first. Of light, it assumed light is made of particles called corpuscles. They have properties of classical particles such as well-defined mass, well-defined size and shape, energy and momentum are also
Okay.
calculated in definite equations. In contrast to
Do I have to
Planck's concept of
explicitly
light.
mention the properties of like
Yeah,
corpuscles?
yeah, that's
Okay.
how like the difference are presented, right? So it's
Okay. I
just
see.
Planck's version of light's particle is like different properties compared to it's really like a different idea. Okay.
Yeah. Okay.
It's not
I see.
just like a little marble, it's really a different mixed wave particle idea. So in
Yep.
Planck's
Okay.
concept, light is our electromagnetic waves with quantized energy, which is carried by quantum particles, which we named as photon. These are more abstract with properties such as they have zero mass, as before we don't have that, and there's no
Mm-hmm.
well-defined size and shape. Energy depends on frequency of the wave. It used to depends on the mass and the velocity, but now it's kind of all different. Yeah, and the
Yep.
momentum is not well defined. It's definitely not modeled by this, and we'll see this in special relativity. Yeah, but it's different to classical particles. Yeah.
Yep.
So this is a quantized idea, not a classical marble-like particle. Okay, so just sort of describe that. You could also draw pictures, right? I didn't draw pictures for this question, but one of the technique that you can do is you can draw pictures. For corpuscles, literally a marble. For
Yep.
quantum model of photons, it's like a little squiggly line, so it's kind of still wavy, but it's also quantized. Yeah.
Okay.
Question 19. Black body radiation thing, yeah. So the graph shows ultraviolet catastrophe, which refers to the fact that prediction made by classical theories of physics regarding to black body radiation has failed with comparison with experimental data. Discuss how classical models leads to UV catastrophe and how Planck was able to resolve it. Okay, so we
Because
sort
they
of did,
predicted that like as the wavelength gets shorter, like like they thought the energy will approach infinity, but that doesn't work. So
yeah. Yeah, we sort of had a very similar question in the examples. But what I wrote for this question is pretty much identical. So you have to emphasize what are the assumptions that classical physics is made to yield this conflict, and what are the
okay.
assumptions that quantum physics is made to solve the issue. Classical
Okay.
models of light assumed electromagnetic wave to have continuous energy distributions in a black body with the ability to emit and absorb all frequency and wavelength of electromagnetic radiation as me defining black body, yeah?
Okay.
Explosions leads to this continuous energy distribution will leads to energy explosion near UV spectrum. This is due to that there are infinite different wavelengths and for each wave an average energy, you don't have to write kb times t, but that's the average energy we put on, is equipartition to every different wavelength. Energy therefore sums to infinity. This is known as the UV catastrophe. You don't have to need that much detail compared to what we did in examples, but this is like a general exam like structure that you could write down, right? That
Okay.
doesn't go beyond too much of the syllabus, but still keep track of everything. Okay. And then the
Yep.
quantum model of light proposed by Planck assume light has quantized energy. These are the assumptions. Make sure you highlight these in your response. Which
Highlight.
are so no, like just make sure they
Underline.
are like the
Yep.
first sentence or something. And I'm not saying that
Okay.
highlight them with a highlighter. Yeah.
Yeah. Okay.
So for each possible wavelength in a black body, energy is contributed by each photon, right? Which is like so many different numbers of photons. And for photons with very large energy, so that means frequency goes to infinity, the number of photons approaches to zero, preventing energy from going to infinity. Okay, and therefore solved the issue. Okay, so
Yep.
it's two key points: a quantized idea, and how n goes to zero as energy goes to infinity, and they together prevents energy from exploding.
Yep.
Question 19b is a calculation question, I bet. Oh no, it's
Yeah.
explanation. Explain the differences between the curves. Okay, they are both black body curves. Differences is because of the temperature, and the effect of different temperature has two uh, changes on the black body curve. Right, the first change is that the peak wavelength will shift. The second change is the area on the curve will shift. So you will just
Yep.
focus on these 2 points. So as labeled, these curves are blackbody radiations at different temperatures. For the 450, you have to support your answer with calculations, so
Yeah, I did that. Yep.
peak wavelength will be very good. So 400 Kelvin, the profile has a larger area under the curve, meaning it's radiating at higher intensity. Furthermore, from Rhian's law, the peak wavelength is dependent to temperature. With that equation, you can substitute it in to get an approximate peak wavelength, yeah, somewhere like 600.
Yeah.
And you sort of repeat that for the 3001, pretty trivial. Okay.
Yep.
Question 20. How does the law of conservation of energy apply in Einstein explanation of photoelectric effect? Um, remember that equation where this thing is sort of derived from energy conservation? You sort of so what this you for this question,
Yeah.
what you need to do is you just need to describe the energy process and construct this equation from knowing that energy has to go somewhere, it cannot just be lost. So the law of the conservation of energy
Okay.
states that energy cannot be created or destroyed. That's like a typical high school definition. In this case,
Yeah.
photoelectric effect, photons carries energy HF, hits an electron on the metal surface. Parts of the energy is used to liberate the electron from work function, which is the minimum energy required. for an electron to escape, and so like any excess energy will be converted to kinetic energy. So describe the energy process is enough. Okay.
Yeah, okay.
Question B. Question B says a student performs an investigation on photoelectric effect using two light sources. Light source X and a wave which has a wavelength of 600, Y has a wavelength of 400. Intensity of both light sources were projected on the same surface is the same. Okay, like I said, so intensity is the same, but wavelength is different. They don't have the same number of photons because the same energy output, one has a higher energy per photon. That means the number of photon here is less. Okay. Describe the differences between light source X and Y in terms of quantum model. So quantum model,
Yeah, just like what you just said, because yeah.
light assume that again it's assumptions. Yeah. Assumed light, so energy of intensity of light is now proportional to the number of photons. You can even calculate that number of photons out if you want. Okay. So for source
Well, you
X,
can. Oh, okay.
you can, right? So each photon has an energy of this much, right? That's just Planck's equation. That's each photon's energy. With the given intensity, the number of photon per unit area per unit time is then 100 as intensity divided by the energy of each photon, which you give 3.02 times 10 to 20 photons incident on each square meter of area per unit time per second. That's a lot of photon on not that much big surface per unit time. Yeah.
Yep.
If all of these photons are hitting an electron with work function less than this energy, you will get this much electrons emitted every second on a meter squared of surface area.
Yeah. Okay.
For source Y, each photon has an energy of this much. You just repeat the process. You can see how the number of photon is less, right? For the higher energy version, but each photon has a higher energy, so it's like with less energy, and Y has less photons with more energy.
Yeah.
So continue question 21. Question says to show that the energy of a photon wavelength this much is this much. Planck's equation, nice and simple.
Yep.
Question B is like calculate how much photon you've got, right? In 0.75 meters squared area, how many photons are there? So you know how the number of photon per unit time is equal to the power multiplied by the area divided by the amount of energy. Yes, so that's how it's defined. Actually, it's intensity. It shouldn't be power, it's just intensity. My bad.
Intensity, yeah.
Let me change the symbol for this. Yeah. So I just do the calculation. It's pretty easy. You can see how it's always like a lot of photons, like 10 to a lot of photons. Yeah. Which means photons is when we quantize the energy of light, each element is really, really small. Okay. This is also the reason that quantum physics is very, very small. It's only feasible if it's very, very small. For very large scales, you have like so much photons, almost like continuous. You know what I mean? Yeah.
Yeah.
A source of light of wavelength this much is incident on a sample of cesium, which has less work function this much. Calculate the maximum kinetic energy. So that's just from the work energy theorem. Sorry, the Einstein photoelectric equation, and you just sort of rearrange for B. All right, so should be quite trivial. Okay, so that's the speed you can get, but be very careful. Many times when you do the calculation with small particles and electrons, because electron is such a small mass, sometimes you would make a mistake and you get a wrong value for speed. You gotta have to know that if this speed like is higher than the speed of light, then you probably did something wrong, right?
Yeah,
so
that's not possible.
Yeah. Okay. Question 22. This photoelectric effect experiment. How did he? So actually, the photoelectric effect is not discovered by Einstein. Einstein was famous at analyzing it.
Yeah.
So how did Leonard measure the kinetic energy of the emitted photoelectron? We use parallel plates configuration, where a voltage is used to like do negative work to photoelectrons to stop them, right? And to measure the stopping voltage where everything is stopped. So that's how it goes. Yeah. Does this make sense? Yeah.
Yeah.
Okay, so question B says, why was the wave model of light insufficient in explaining the results? In your answer, refer to two specific experimental observations. So again, you want to emphasize what classical assumption is and what would classical physics predict and what did we actually observe and how quantum solved it. Classical wave model of light assumed light is electromagnetic wave with continuous energy distribution associated with amplitude of the radiation. Okay, this allowed for accumulation of energy. Okay, so experimental results included the following aspects. The first one is that we found an existence of threshold frequency, which means for a particular metal, photo emission only happens when light is above some threshold frequency. This contradicts classical assumption where electrons can just accumulate energy enough so that they can escape, and you would corresponding to some time delay, but this was not observed. Yeah.
Yeah.
So yeah, that's one thing. And then the other thing is energy of photoelectron is found to be independent to the intensity of the light. Right? If you increase the intensity, the energy of photoelectrons remains the same. Okay, so varying brightness and of intensity of light does not affect the energy of photoelectrons emitted. So this contradicts the classical assumption where they thought light has higher intensity, is like more energetic, they have a higher electromagnetic wave amplitude. So upon interaction with electrons, they would like get more kinetic energy from it, but was not seen in the experiment. Okay. Question 23. Again, this is a graph question of photoelectric effect. Right, 4 different frequencies of light being used. Be very careful with this scientific notation scale when you do the gradient calculation. Please involve that as well. And then the y-axis is labeled with Kmax. Did you do that? You probably forget.
I didn't get up to this question.
It's fine. So Kmax is like these values. You just graph it. Make sure to remind yourself that this is in units of electron volts. Okay.
Yep.
So 1 eV was 1.602, 10 to the negative 19 joules. Okay. You just graph it. It's a nice straight line. Pick 2 points to get your gradient. Question B says to calculate the Planck's constant. So we know that this graph has a gradient representing the Planck's constant, but because the y-axis has been sort of changed rather than just doing the joules energy version, yeah. So the gradient sort of also has like a different units as well. We're gonna have to convert everything. Okay, so the theoretical relationship is modeled by the following equation. Right? So we actually plotted EK as well. So the kinetic energy is it used to be HF multiplied by phi, but now it's sort of like because everything is in terms of EV, so it's sort of like the normal joule energy divided by QE. So you can construct the equation like such. Okay, so that the gradient now only represents H over QE.
Okay.
So the gradient is therefore this, and then you want to solve for the Planck's constant, which you're not getting this value, which is quite good.
Yep. Okay.
So anywhere around this value should be fine. Okay.
Okay.
Again, be very careful of this thing. Yeah, people forget about this. Like 2 out of 8 people know how to do this, right? I mean, 2 out of 10. So 8 other students will like just forget about this and getting it wrong. Okay. Calculate the work function of the metal used in this experiment. Okay, so that's just this thing. Yeah.
Yep.
But you can't just interpolate this graph because you see how the x-axis we started from 0 and jumped to 8 and it's squiggly lines here. So it's like it's not linear across like these regions, so you can't just extend it and find the y-intercept. Okay, so the work function is the y-intercept, by the way. Yeah, but we can't do this. We can't just do this. It doesn't work. Okay. So what do I do instead is like we use, because we have just found the gradients. And we also found we can find points on the line of best fit. With a gradient and 1 point on the best fit, we can use the point gradient formula to get this equation in terms of its gradient and an intercept formula. Okay, so we just use that method to determine this. Okay.
Yep.
So the work function would be the y-intercept, but the format of the graph makes it impractical to interpolate. We find the y-intercept by subbing a point in the line of best fit. Okay, so work function over Q is this thing. Yeah, and then we put in a value of frequency corresponding to a value of EK, which I picked this point. It's just one of the point above this one. Okay.
Yeah.
Make this substitution, solve for it, and you'll get your you'll get your work function expresses electron volts, which is simply just this thing together. Okay.
Yeah.
It's
Okay.
2.93 electron volts. Okay. Like this question, when I made it, is like a bit. So usually in HSC they don't have like such something like this. They don't. This I don't. I've never seen HSC questions as anything like this. So usually you would just interpolate in HSC. Okay, it works. You just extend the line and be like, oh, yeah.
Okay, so I just gotta watch out for the scale. Yeah. Okay.
Yeah, this is a bit unfriendly with general with like center math students, so they try not to do that.
Yep.
Actually, I recently found out when they do the plotting questions, usually they don't do anything with like except for photoelectric effects. Anything else with like those graphical questions, they avoid doing models with y-intercept, so that's kind of like weird.
Oh, okay.
Question 24 is talking about light of wavelength 400 nanometer is incident on a different metal inside an evacuated tube as shown. Some of observations from the experiment are shown. The current reading is recorded as the following. Okay. So zinc work function is this much. There's no current reading, and for lithium, a smaller work function, there is a non-zero current reading. Okay. So my graph looks like this. Okay. So the zinc has no current no matter what intensity there is. Lithium has a constant current. Right. You see a red dot here. That's because I have the original version for this graph was wrong. So I have to modify, but your version should be fine, yeah?
Yes, I think so. Yeah, it's fine.
Yeah, so I've just sort of hide this red line. So yeah, so that's what I mean. Okay. So how do the experimental results support one model of light? So the fact that if you increase intensity, zinc stays at 0 and lithium increases linearly would support the quantum model of light. So the graph indicated that the intensity increases, the size of current increases for lithium, but for zinc, no current is detected whatsoever. This phenomenon supports the quantum model of light where energy of the electromagnetic wave is quantized and carried by photons of energy this much. Photon emission is essentially modeled as one-stop collision. So if you just increase the number of photons, if it doesn't have enough energy, nothing's going to happen.
So not do nothing. Yep.
Yeah, so photons need to have at least have enough energy to overcome the work function, and you can do this calculation as well because they give you the number, right? You can tell you the wavelength as well, so you can compare. Okay, so you just did that.
Yep.
For zinc, work function is this much, which is greater than energy of each photon, so no photon emission collisions is failing. Okay. For lithium, it is enough, so it happens. Okay, so that's good.
Got it.
Moving on, question 25. It's an experiment conducted using photoelectric cell. Again, this is a forward potential, right? Be very careful with the direction of this. So it's not slowing down these electrons, but it's accelerating them. So our mathematical model changes. Okay, how much work is done by the battery from the photoelectrons? This is module 6 knowledge, right? Work done by parallel plates. So just Q times the voltage between. Yeah. Just this much. Because we have learned EV, so it's kind of easy, just 5.2 EV. Okay, so it's really good. Yeah, so the graph shows maximum kinetic energy of the emitted photoelectrons against radiation. We've got two graphs. Actually, you've got one graph, and the other one is like supposed to be drawn by yourself. Yeah. So the experiment is planned to be repeated with a voltage of 0 volts. Okay, so now I'm not applying any volts here. No more potential to accelerate these electrons. Yeah. Draw a line on the graph to show the predicted result and the planned result. Justify your answer. So really, you gotta. So in this situation, in the situation before when we have the stopping voltage, the equation goes like this: HF minus phi. Now it really isn't like this. Okay, because the potential is now different, so you sort of have like negative QV plus the kinetic energy equals to HF over phi. Does that make sense? Because like the potential is different. Yeah.
Yep.
So
Kind
you
of.
really
Yeah.
gotta rederive this equation. See, this is an extra term, as in like photons energy take your work function, and you also put in some energy with the voltage. So the K
Okay.
max is
Okay.
gonna contribute from that. Yeah.
Okay. Okay.
So what you're really graphing here is you're
Oh.
graphing this thing. You're graphing this equation. It's like
I see.
your
I
like your
see.
y-intercept is no longer just work function, is negative of the work function plus some positive value. So it's been shifted
Okay. Okay.
up.
I get it.
That's
I
why you
get it.
get
Yep.
a zero y-intercept. Yeah.
Yep. I get it
So
now. Yep.
exactly pulling this. So this graph is when v equals to 5.2, right? It looks like
Mm-hmm.
that. But if you turn off v, this term goes away. You would shift everything down 5.2 units. So that's what really happens. Okay. So
Mm.
now when the applied voltage turn off to zero, which we have that the normal equation. Yeah. So we have a
Mm-hmm.
graph with identical gradients because the gradient doesn't change,
Yep.
but shifted downward. To sketch this graph, we need a point, right? So we, for every line, what we plot on xy plane, we need its gradient, which you already know, and we need a point, right? Point gradient formula,
Yep.
right? So we need a point. So what point can we use? Let's let this point be the threshold frequency, right? Because at that point k is zero, so it's good. Yeah.
Mm-hmm.
Which is just the x-intercept, right? So by definition, the threshold frequency is
Mm.
the work function over h. So you find it, right?
Okay.
Uh, no, substituting
Mm.
f equals to f0. I've made a typo here. Okay, so
Mm.
and in
Oh
equation
yeah.
one, which is this equation, and you can solve for it, okay, which is this much, and you just
Yep.
find it on the axes, right? And then you just draw the same curve with the same gradient. Okay,
Yep. Okay.
good. Question 26. It shows a spectrum of star. It looks resembling a black body spectrum, but you get those imperfection absorption lines, right? So Y would be like less intensity. That means those lines, those locations are being absorbed by specific atoms or something. Okay.
Mm-hmm.
To calculate the surface temperature, you locate the peak wavelength, which is roughly 400, and you do that. Wien's law, easy. Okay.
Yep.
B wants you to explain the features of Y, and these are, like I said, absorption lines. To just explain that. So the features labeled indicated a reduction of intensity,
Mm.
which would imply absorption took place at these locations. Thus, these correspond to absorption spectrum of a star. Okay, and
Yep.
how are these features, which are absorption lines, can provide information about chemical position and density? So just explain that, right? The
Mm.
relative positions of these lines are characteristic to different chemicals as they each corresponding to a unique electron energy state transitions. I would say that.
Mm-hmm.
Okay, and the next point is like the Barney effect, because if you want to look at like the thickness of this or like the width of this line, right, be able to indicate its
Mm-hmm.
density. Yeah, indicate for density.
Okay.
The denser the star, the more collisions between atoms, causing
Yeah.
more random perturbations to the energy states and making the spectral line thicker but
Mm-hmm.
blurry because it's all random. Yeah.
Mm-mm. Okay.
27 and sunlight and light. Okay, charge tube. So it's like one radiation with the line happening, right? So you're gonna have black body as an absorption lines.
Mm-hmm.
Are you gonna absorptions and the gas discharge two spectrum? Like we heat it up or we of radiation from the sun, which is considered as a near perfect black body. Chemical structure stars alternate will absorb certain into their states. A gas discharge tube, on the other hand, consists of vapor of atoms such as metals or noble gases. Okay.
Yep. Hello?
Hello,
Hello?
hello, I'm back.
Hello?
Do you
Yep,
hear
okay.
me now? Yeah, the
Yeah,
Wi-Fi fucked me up. Okay, that's fine.
it's okay.
Let's continue. So, like I said, so a gas discharge tube, on the other hand, consists of vapor of atoms such as metals or noble gases. Under a large applied electric potential, these electrons in these atoms gets excited as like and quickly decays back to produce emission spectrum. And
I
those
don't think
lines
your
would.
screen sharing, by the way.
Oh yeah, thank you for the reminder.
Okay.
Okay. So yeah, and they're excited and quickly decays back, right? So they would produce spectral lines corresponding to their emission lines. Okay.
Yeah.
In terms of question 28, so sample of hydrogen gas is heated. It produces the following spectrum of light. So you've got those emission lines. How does the spectrum relate to the behavior of electrons in Bohr's model of the atom? In your answer, make references to Law's conservation of energy. So, so just basically how like Bohr's model of atom predicted, like why do we have spectrum, right? So Bohr's model, so you just define their postulates. Bohr's model of the atom has postulated rules for electrons around the nucleus, right? The first postulate says the electron only exists in stationary states, not in between. So the energy of the electrons are discrete, and you can draw a little diagram for the energy states. It's kind of like every state. And then transition jump up requires a photon, jump back down releases a photon, right? So that's the second postulate, right? Electrons can transit between stationary states with an exchange of photons of corresponding energy. Emission spectra are produced in this case where the heated H atoms converts heat energy into electron and becomes excited to a higher energy states. They become unstable and quickly decays back to the original states. So the energy is conserved as a photon carrying energy. The energy difference is emitted during the transition. Okay, so you want to also talk about loss function energy. So describe energy transition processes. Okay.
Yep. Yeah.
Okay.
Okay. Got it.
Last few questions. Okay. Question 29. Spectra of light. You've got 3 different absorption spectrum. This is one for hydrogen. This is one for helium, and we've got another one for a star. Okay. Account for the black line. Okay, although here are really white lines, but it's supposed to be black in the spectrum. So first of all, these are absorption lines, indicate that. And each of these lines corresponding to a possible electron transition between energy levels. Okay. And they are produced by radiating a black body spectrum with all wavelengths of radiation onto a sample of hydrogen or helium, respectively. So the atoms then picks up specific photons of specific energy, matching their energy state differences. And then that lowers their intensity, right? Which means you will see a darker line there. Okay.
Yeah.
That's how it's produced. Question B, use the information provided, analyze the chemical composition, surface temperature, and the motion, right? This again is like you look at this graph, right? So we see it resembles the relative position of the lines resembles helium. We don't see any hints of hydrogen, right? And then the lines are thicker, so that means there's rotation. So you can
Yeah,
just talk
okay.
about that. So star spectrum reveals important information about surface temperature, chemical composition, and as well as motion. For surface temperature, notice that the question give you the peak wavelength. Yeah.
Yeah.
Then you can use Wheeler's law to calculate for temperature, 3,500 Kelvin. For chemical composition, is really like very similar to what we already talked about, right?
Yeah.
For translational velocity, you can just say, again, translational velocity, you can see how, like, if you compare these lines, this one is slightly more redshifted. So this star is probably moving away from us a little bit, okay?
Okay.
So you just mentioned that. So translational velocity can be seen from systematic shift of spectral lines. When compared with helium lines, the lines from the star systematically shifted towards larger wavelength, which is redshift, indicating the star is moving away from us. And similarly with the rotational speed, right? And sort of just explain how this corresponding to the motion, right? Since half of the light is redshifted and half of the other light is blue shifted, together this will result in a broadening effect, okay?
Yeah. Okay.
So just a few notes with the challenging question, yeah? So the exposure of photographic film uses light-sensitive compound called silver bromide. This compound, the amount of energy to sort of expose, right? So this is like photography thing. The film is this much per gram of the substance. Okay. One
Okay.
single bromide molecule has a mass of this much. Question A says to find the energy and the wavelength of photon required to expose one molecule of silver bromide. Okay, so you just find out the energy. This thing times that, right? That's energy required for one molecule of it. Okay, and then use
Okay.
this energy to find out how much wavelength do I need. That's just Planck's rule. Okay.
Yeah.
And if
Okay.
you are observant, you should know that this wavelength corresponding to an IR spectrum. Yeah, so you would really need IR radiation or anything above IR to do this exposure. So
I
this
see.
experiment resembles resembles the same effect as photoelectric effect, where you have light inducing a photo
Okay.
emission. This is light inducing an expose, right? Same thing, right? Each
Okay.
photon
Yeah.
induce one molecule to expose. You want a photon with a higher energy than IR to do so.
Yeah. Okay.
Now, question B says to explain why. So you've got a light bulb that's like 1 watts of like sort of power or intensity, and a TV tower has like 1 kilowatts of power or intensity, right? And why would 1 watts of light bulb be able to expose it, but a TV tower can't do it,
Okay.
even though it has more energy? So it's kind of like
Okay.
similarly
Okay.
as photoelectrons, right? It's like, oh,
Ah.
why can't a brighter light produce like higher energy of photoelectron? Same thing as well, because like each photon has less energy in the TV tower. So light
Okay.
has quantized energy. The light bulb is considered as a black body emitter, so it has all frequencies of it. So it has a lot of IR and anything above it as well. So of course it's gonna be able to expose it because black body, everything is there. Okay. But then the
Okay.
TV tower, on the other hand, operates primarily in radio frequencies. Do you know this? Like, do you know that this is a
Kinda.
fact, right?
Yeah. Yeah.
So we transmit information using electromagnetic wave primarily with radio waves, which is like the
Yeah.
longest wavelength spectrum. Yeah,
Yeah.
longest.
That's why it's called the radio.
Yeah, it's
Isn't it?
super weak energy photons are distributed in the radio waves. That's why AGBR will not affect by the radio waves sent by, even though there's a lot of radio photons, but they are all weak. Okay, not enough.
Okay.
Question 31 is coming up in the new syllabus. Okay, I've checked it. See, like a lot of the extension material is just like really just high school level. They just not yet in the syllabus. Okay.
Okay. I
This thing
see.
is, I mean, not equation, but the concept. Okay. So
Okay.
the spectra of stars are closely. So we've talked about spectra of stars and how it relates to the chemical composition and temperatures, right? There's a subtle detail to this. Okay, so certain spectral lines are visible at certain temperatures. So if a star with of very high temperature, some of the spectral line will sort of disappear, and some of new spectral lines will reappear. Okay, now this is not because that the star doesn't have the elements of the corresponding disappearing spectral lines. It has and it could have a lot of it as well. It because
Okay.
of many different reasons, and this question explores it. Okay.
Yeah.
For a given atom in initial state A, right? So like an atom has an electron in initial state A, and a different
Mhm.
and then at a different state B, that's just electron configuration. Yeah. The ratio of the atoms
Yep.
that are in
Okay.
those states can be affected with temperature. Say that a hotter star, you would expect that the hydrogen atoms in the star would mostly be excited. Yeah, you would expect
Yeah.
that. Yeah,
Yeah.
that's
Yeah.
this equation allows you to calculate the ratio based on the temperature of the star and the energy state differences, and how
I
many
see.
electrons that you can fit in that sort of state. Right. This is called a degeneracy constant. And just some of the atomic physics side of view, these are like the equations for those things, right? And you will learn this in module 8 as well, so it's fine. Where n being like the energy levels, okay? Now this means that for the first ground state energy, you can only fit 2 electrons. In the second
Okay.
excited state, you can fit 2 times 4, which is 8 electrons. Does that make sense? I mean, if you study chemistry, you would be very
Yes, kind
familiar
of.
with this 2-8-8 electron configuration, which is exactly
Unfortunately, I don't.
come from this degeneracy state of quantum mechanics.
I see. Okay.
So using
Kind of get it.
so you can just use the Boltzmann equation, get a substitution of these numbers in, right, and then use neutral hydrogen of ground state in the second shell. So that's n equals 2, n equals 1. Plug everything into these equations, right, and then you can get a ratio. So for 50,000 K star, the ratio is 2.67. So the unexcited hydrogen is more like preferable than the excited hydrogen, right? So it's like 3 of the hydrogens, only like 1 of them are like, excited. Okay.
Yeah.
But then if you increase the temperature by 2 times, right? This ratio becomes
Uh-huh.
0.82, which means that there are more excited hydrogen atoms in there. Which means that we should see special lines according to the second excited states as a preferred one. You know what I mean? Yeah. For this hotter
Yes.
star, right?
Yes.
This is what we expect
Yeah.
to find. However, real observations has indicated that it's not really the case. This hotter star actually doesn't even have any hydrogen spectra anymore.
Oh.
And why is
Oh,
that?
okay.
This question wants you to explore that. So that doesn't mean that the star does not have hydrogen. So star is made of hydrogen, definitely has hydrogen.
Yeah.
We don't see the lines, or the lines gets really dim, is because that at this hot temperature, hydrogen atoms cannot hold their electrons anymore. Electrons simply just evaporates and escapes and ionizes, right? They're no longer in the in a potential. They escapes. You can escape velocity as well. They just escape the nucleus potential. All right, so
Okay.
there's no more electron transiting between states because they all just escape, right? So
Yeah, they
there's
just
no more
go.
lines
Okay.
because of that. Okay.
Oh, that's fine. Okay. Okay.
Yeah, and this will be in
Interesting.
the new syllabus. They
Ah,
will
man.
be doing more astrophysics in the next syllabus. Okay.
Well.
So this is called the Saha equation. The equation that allows you to
Mhm.
calculate the intensity of these lines, or Saha equation. You can research this,
Ah,
okay, if you like
yeah.
this. Okay.
Sounds interesting.
Right. Anyways, that's it for this booklet.
Yep.
I will see you next time then.
Yep. See you next week. Yep.
Yeah.
Bye bye.
Thank you.